a 4 centimeter times 8 centimeter rectangular coil with 120 turns carrying 0.5 milliampere current is placed in uniform magnetic field 0.3 Tesla. Calculate required torque to hold the coils plane parallel to the field. So now if you have the, let's say this is a direction of the magnetic field B, right? And you have a rectangular coil, the planes parallel to the field, magnetic field, meaning you have a parallel coil with how many turns here? We have 120 turns. So the area here is here. This is A, and the current here is 0.5. The current flow here is a 0.5 milliampere. And to calculate the torque, the equation for the torque here is equal to B magnetic field B times current flow times number of turn N and the cross-sectional area A, and this is sine theta. The theta is angle between B and A. B and A here is a 90 degrees, so meaning the theta here is equal to, this is equal to 90, or this is equal to 1. So torque is equal to B, I, and A. Next, the magnitude of the P is given by the question is equal to 0.6. So this is 0.6 Tesla, and time the current flow is 0.5. So 0.5 milli is times 10 power of minus 3 ampere, and the N here is number of turn is 120, and the area A is equal to, so now you have a 4 and 8. So meaning the value of the area here is a 4, this is centimeter, is meter, is minus 2 times 8 times 10 power of minus 2. So this is area A. So if you calculate here, the A is equal to 32 times minus 4 meter square. So now this A here is a 32 exponent minus 4, right? Okay, so the value of the torque to hold the coil plane parallel to the field is equal to 1.152 exponent minus 4 Newton meter. The next question B, a 1.35 exponent minus 15 kilogram particle of charge 5 nanocoulomb and velocity 3,500 meter per second enter a region uniform magnetic field 0.25 exponent minus 2 Tesla perpendicular to the field. Then you have let's say this is a test particle with a mass 1.35 exponent minus 15 kilogram enter to the region. When the region have a magnetic field, let's say this is a magnetic field into the page. So when the particle enter to the magnetic field B is 0.25 exponent minus 2 Tesla. So now you have the positive charge here. Okay, with the speed is V is 3,500 meter per second, and so if you use the left hand left hand. So you have this is the thumb is a your thumb is a force, and your first finger is a direction of the B, and the second finger is a direction of the V, right? So this is a 90 degree, it's 90 degree, right? So now the direction, because B enter to the page, because this is enter to the page, so B enter to the page, and the V is to the right direction of the V to the right here, and for the left hand the direction of the F is to, okay, the direction of the force F here is to upward. So when the position of the charge here, okay, so the force is to the same process, and when the charge is here, the force is here, meaning if you draw the path of the charge when enter the magnetic field B, the path of the positive charge here is like a semi-circular path, right? So this is direction of the positive charge when enter region B. So this is looks like the circular motion. So meaning if you relate to the circular motion equation, it is a first semester centripetal force acts on the positive charge here and here to the center, or FC here. Centripetal force is a mv squared divided by r. And if you use this is the first and second, this is the left hand, because combination magnetic field B, velocity of charge V, you can produce force here. The force here you can use the equation QVB. So now the magnetic force as B is equal to Fc. This Fb is equal to QVB. So now you can use the equation here. mv squared come from the centripetal force, and magnetic force X on the charge is QVB. So now you have a mv squared divided by r, and this is equal to QVB. So now from the combination to formula or equation here, so you can find the value of r here. So you can use the value of the r is equal to mv squared divided by QVB. And the next is because V here is the same value, so now you have a mv divided by QB, and the value of the mass is given by the equation 135, and the V here is given is 3500 meter per second, and the charge Q is 5 nanocoulomb, and the B given by the equation 0.25 Tesla. So you can use the calculator to find the value of R is equal to 0.378 meter. So number 2, explain whether there is any change particle path when the magnetic field reduce half and particle velocity increase 4 times, meaning initial B, and after reduce half, or B come to B over 2, and the value of the speed V is increased 4 times. This is for V from initial value, right? This is initial B. So if you look at the equations, the radius R is from the first answer, first calculation r. This is just a small r. Sorry, use the small r here. Radius r is given by the equation mv divided by qb, right here. So now if the value of the b is become to the b over 2 and the v is increased for v, so if you calculate the value of the mass of the v of the b, but this is half and this is 4 times increase, and the value of charge 5 nanocoulomb, the value of r is 8 r, sorry, this is equal to 8 r, meaning the value of the radius is increased 8 times compared to the initial value when you decrease of magnetic field B half and increase the velocity of the particle 4 times from the initial value V. Thank you.